Okay, guys, welcome to our podcast on bioremediation. This is a discussion on how microbial activity can be harnessed to extract useful components from the environment or to remove toxins in order to reclaim things like groundwater, soil, and land that's been purposed for industrial uses. So, microbes are involved in nutrient production and energy flow, decomposition, and biotechnology, where they've been harnessed in the production of food, drugs, and vaccines. And they've also proved valuable in genetic engineering, essentially as vehicles for the amplification of DNA and also to improve the ease with which DNA can be manipulated. Bacteria serve as DNA factories in a sense, allowing us to introduce artificial constructs, amplify them to the desired levels, extract those constructs, engineer them, and then regrow them using the bacteria again as a vehicle. And then that genetic material can be utilized for downstream purposes, such as producing transgenic animals, or perhaps in the bacteria itself, it can be used to generate a particular drug via the production of a transcript that can make a protein that provides a valuable service. Um, any variety of applications are possible here. But today we want to focus on its role in breaking down toxins in the environment, and also sort of an ancillary to that, the ability to sort of harness or use components of bioremediation to extract valuable components from the environment. We also know, of course, they're involved in infectious disease, and we've discussed that several times over the course of the past several weeks. So, environmental microbiology is the study of microbes in their natural habitats. Applied microbiology is essentially putting the microbes to work generating a product that's going to be useful in everyday life. For instance, food processing, industrial production, or biotech are just a number of examples where the microbes can be harnessed to generate something useful in each of these fields. Microbial ecology studies the interaction between microbes and their environments involving living and non-living components. The living components we call the abiotic component of the ecosystem, and the living component is the biotic component. So let's label that so that we know. Okay, the living component here, the biotic, and the non-living, the abiotic. So this is just some examples of how bioremediation is impacting our daily lives. Here we see copper extraction from adulterated ores. A lot of commonly occurring low-grade ores are nitrates, sulfates, or oxides of precious metals or semi-precious metals, and in lieu of chemical processes to reduce these low-grade ores into their ecologically and economically valuable components, we can use bacteria by harnessing their ability to reduce adulterated ores in normal microbial metabolism. We can generate essentially microbial mining. Here you can see copper extraction at work. We can do the same with iron and any number, again, of semi-precious metals. Wastewater treatment is something we're going to go into in a little bit of detail today. This is something that impacts our life every day. If wastewater isn't properly treated before it's reintroduced into the groundwater or into the surface water, then we can see an increase in the number of toxins and pathogens that have to be removed when the water is rendered potable. So by treatment, we cut down considerably on the work at the other end of water purification, which is the generation of our drinking water. And then we see here bioremediation in oil spills. And we're going to actually do a version of this in lab, working with our oil-eating bacteria using different pHs to try and determine which pH the oil-eating bacteria were most effective at. Bacteria degrade organic matter in sewage. They do this by oxidizing these compounds. They serve essentially as fuel for the bacteria because they contain carbon-hydrogen bonds. And we have to remember that the carbon-hydrogen bond is the money bond in terms of energy content in living systems. So the more carbon-hydrogen bonds a compound has, the more chemical potential energy it can provide for that particular organism, provided, of course, it has the enzymatic machinery to take advantage of it. Bacteria can degrade or detoxify pollutants such as oil and mercury. The mercury is an interesting aspect of this. The bacteria won't necessarily use the mercury as an energy source. They might reduce adulterated mercury ores in an oxidation reduction reaction that generates a useful fuel for them biochemically. The oil can serve directly as a fuel source for the bacteria because oil represents probably in nature one of the greatest stores of chemical potential energy known to man. And all you have to do to understand why oil has so much energy in it is just to look at the structure of a typical long-chain hydrocarbon, and what you'll find is an abundance of carbon-hydrogen bonds that's not equaled really by any other compound on the planet. And for living systems, not to mention our economy, this represents a huge boon. We're going to talk also about wastewater treatment, and we'll compare and contrast the processes that occur during primary, secondary, and tertiary treatment. We'll explain how septic systems operate, and we'll ID at least 2 challenges for the future of wastewater treatment. So this is a nice little overview of wastewater treatment. It deals with both the mechanical aspects and the biological aspects of rendering our wastewater safe to reintroduce into our groundwater or into our surface water. So take a listen.
The second we flush, it's all over for most of us. For others, the process of treating wastewater has simply just begun. If you've ever wondered where it goes, but more importantly, where it ends up, we will attempt to answer that question by taking you through the entire process, flush to finish. Every home and business uses water and generates wastewater. Once waste is flushed down a toilet, it travels down a lateral into a main pipe where gravity begins the process of the flow toward the wastewater treatment plant. The wastewater travels through miles of pipe before eventually arriving at the plant. The city's wastewater plant treats wastewater from residential, industrial, and commercial customers throughout the city. The plant cleans the sewage and eventually discharges to a ditch, which eventually drains to the Wood River. The water is treated to standards set by the DEQ and in many respects is very close to a drinking water standard. As a part of the permitting process, the facility samples all of the wastewater entering and leaving the plant. Portable refrigerated samplers are on site to meet that standard. Not only do they sample the raw wastewater coming in from the community, they also sample the JBS flow as well. When gravity is doing the work of carrying sewage, it's considered a free service. In an ideal scenario, gravity carries the sewage from the home all the way to the treatment plant. Because of the nature of our flat terrain, the gravity sewer mains eventually become too deep for practicality, and the wastewater must then be lifted by means of a pump at what is called a lift station. The term lift station comes from the process of using a pump to lift the sewage up in elevation to allow gravity to once again begin its work of delivering the sewage to the treatment plant. As wastewater enters the treatment plant, it flows through a bar screen to screen out large solids. It's amazing what can come through the wastewater collection system. Plant staff has reported over the years finding numerous diapers, 2x4s, bricks, underwear, toys, and even false teeth, which the owner did in fact want returned. A mechanical rake system is used to keep the bar screen clean. This chain, which operates the rake mechanism, helps filter out the trash, separating it away from the wastewater. The rake dumps the solids into a bin inside the station, manually cleaned out, and is later hauled to the landfill. Take a look at the bottom of this rake mechanism. Over 45 years of wear and tear has caused the bottom supports to rust through. Staff had to re-engineer and fabricate a piece of 1.5-inch channel iron to replace the existing support to keep the mechanism operational. Purchasing replacement parts for this equipment is not an option, it's too outdated. Examples like this show just how valuable it is to have a skilled staff in place to address a variety of fabrication challenges. Part of the wastewater treatment plant's capital improvement plan is a project to construct a new bar screen and rake mechanism. Rather than manually having to clean the mechanism, as they do today, an upgrade would automatically shred, compact, and wash the waste, drying it into a very fine material which would then be hauled to the landfill. Over the next 2 years, the facility is aiming to become a cleaner operation by installing a much finer screen into this part of the process, which in turn will filter out more waste and reduce wear and tear on the pumps at the plant. Wastewater continues through the bar screen and into the wet well, where grease balls begin to form. Simply put, grease that is dumped down the drains and empties into the sewer system will form a ball around any solid waste item in which it comes into contact. An example would be grease forming around a cigarette butt or dish rag. As it forms, these grease balls can become larger and larger and eventually have to be cleaned, which requires staff to collect the grease balls every few weeks. If they are allowed to get too big, they have been known to plug pumps and cause a variety of damage. You can never tell by looking here, but wastewater is actually 99.8% water and less than 0.2% solid material. Once the wastewater enters the facility, we dive a little deeper, if you will, into the pump station wet well. We are now down 15 feet below grade, or below the ground. The sewer which brings all the wastewater in is closer to 25 feet below grade, or below the ground, which means there is 10 feet of raw sewage under our feet at this point, 5 feet of open air, and another 10 feet of raw sewage. The pumps on the other side of this wall pick up the sewage and take it to what is known as the headworks part of the facility. There are 18 sewage pumps which pump raw sewage out of the city and into the wastewater treatment plant. The raw wastewater pumping station at the plant is the largest lift station in the city of Grand Island. It consists of 5 main pumps with a capacity to pump up to 40 million gallons of wastewater a day. The ability to continue to pump wastewater every day is critical. That's why this main pump station has 2 sources of backup power in the event of something going wrong. The 18 lift stations throughout the community are also designed with backup power sources. This design and redundancy is to prevent sewage backup in our basements. In a worst-case scenario, a complete system failure of this lift station would be detrimental to the city of Grand Island. Although there is some capacity in the collection system, the inconsistent slope of the terrain and the different areas of town would cause some basements to back up in a matter of minutes and others in 2 or 3 days. For this reason, the level of redundancy is spread throughout the plant to ensure the community can continue to operate. This pump station was built with the original plant in 1965. Through maintenance and ingenuity of plant staff, they have found a way to keep the equipment operational for almost half a century. Without exceptional fabricating ability and annual maintenance, this equipment would have been replaced some 20 years ago. Something else of note, in 2008, over 50% of the plant's inflow was from infiltration and inflow, or I&I. Infiltration is groundwater finding its way into the collection system through every crack, crevice, or leaky pipe it can find. Inflow is rain finding its way into the collection system, or a basement dewatering sump which is discharging into the system. In 2008, during a period of heavy rain and flooding, the plant registered a peak flow of 38.5 million gallons per day for a span of 15 to 20 minutes before it leveled off at 35 million gallons per day. The peak instantaneous flow design for the facility is 40 million gallons per day, so it's easy to see how quickly I&I can affect a plant at a moment's notice, taking it to capacity. This 16-inch pipe stretching horizontally across the wet well is the JBS sewage flow. This meatpacking plant has a flow that comes in separately from the rest of the community. In a town close to a population of 50,000 people, this meatpacking plant is the largest single customer, discharging up to 4 million gallons of sewage per day. In the late summer months of 2010, the city's wastewater facility was averaging 12 million gallons a day, with 3.5 million gallons of that flow belonging to JBS. Not only are they a large percentage of the daily flow, but have been known to contribute over 50% of loading on some days, thus requiring a separate flow. This is the upper level of the dry well side of the raw wastewater pump station. It contains all of the electrical equipment and the motors to drive the pumps down below. There are 5 main pumps, 3 of which are driven electrically, the 4th can be driven with a diesel engine, and the 5th can be either electric or diesel. Again, the diesel and electric redundancy options are built in to keep the wastewater moving through the facility. There is a 100 kilowatt diesel engine generator located outside, which can provide electricity to power the entire pump station if needed, along with the capability of using 2 of the plant's main pumps operating on diesel power. The first 2 pumps on the left can move from 5 to 7 million gallons per day of wastewater. The far 3 pumps can move anywhere from 8 to 14 million gallons per day. The system is designed to maintain a constant level in the wet well by use of a bubbler control system. The bubbler measures the depth of the wet well and in turn adjusts the speed of the pumps accordingly, pumping sewage to the headworks of the plant. Once the wastewater leaves the pump station, it travels here to what is known as the Partial Flume, named after a French scientist who was instrumental in its development. This attachment protruding from the concrete may not look important, but it might save your life. JBS uses an anaerobic environment for the pretreatment of their wastewater. As a result, they convert a lot of their sulfate in the water to sulfides. When JBS combines with the rest of the community's wastewater, it can make hydrogen sulfide, which has a very strong scent similar to that of rotten eggs. This situation becomes dangerous when high concentrations of this gas exceed 200 parts per million or milligrams per liter, and can cause paralysis to your breathing system. This meter is constantly taking measurements of the air and reporting back to a digital readout with a constant log. In addition to keeping staff informed as to a potentially life-threatening situation, it also alerts staff to hydrogen sulfide levels that can be considered offensive in the community. At that point, corrective action can be taken. The Partial Flume measures the wastewater and then splits it into 2 parallel flows to one of 2 grit basins to remove sand, gravel, and other gritty material. Each grit chamber is 10 foot wide, 12 foot long, and 15 foot deep. The basins are sloped toward the center so all the heavy materials move to the center, settle, and are removed. This facility will pull out up to 2 cubic yards of grit per week, almost enough to fill a normal-sized pickup. Heavy rain events can double the grit because of I&I. Next in the process, wastewater moves to the primary clarifiers. The primary clarifiers are speeding up the process of Mother Nature by allowing solids to settle out. If raw sewage was dumped into the environment, be it in a lake or river, the first part of the process that would take place is the settling out of solids, exactly what we see happening here with the primary clarifiers. The primary clarifiers are a 75-foot diameter tank with a sloping bottom where primary settling occurs. The outside depth of the tank is 7.5 feet, while the center depth of the tank is 10.5 feet. To promote settling, the flow of wastewater is slowed through the tank, taking from 60 to 90 minutes to flow through. The primary clarifier mechanisms were replaced in 2010. The skimmers you see going around the tanks are only a very small part of that mechanism. Down below is a very large steel framework that moves around the tank. At the bottom of the mechanisms are scrapers that work with the slope bottom and move the solids to the center of the tank for removal. The solids are pumped off using a progressive cavity pump to a holding tank where they are kept fresh by adding air. The water that comes off the primary clarifiers has 25 to 50% of the suspended solids removed. So we began the process with the flush. It carried through the city mains, across the bar screens, through the wet well, into the main pumps, past the grit basins, and out of the primary clarifiers. We have now completed the primary treatment process and are now ready to move on to the secondary treatment process. An interesting side note, on a typical day the facility will remove 10 to 15 tons of suspended solids and BOD. Biochemical oxygen demand, or BODs, is a method used in the scientific community to measure the biological strength of the wastewater to use up or demand oxygen. That method is also used here at the plant. The Grand Island Wastewater Treatment Plant makes a concentrated effort not to use any artificial chemicals or treatments throughout this process. They are simply growing the bacteria, or bugs as they call them, found in nature. The bugs begin to eat the raw waste in the water. By growing these bugs in a controlled environment, they accelerate the speed of a process very similar to what Mother Nature uses to clean water. This type of treatment, using bacteria, has been used in the United States since the late 1800s. The first wastewater treatment plant in Grand Island was constructed in the early 1920s, where the Brudick Power Station now resides along Cherry Street. Construction started in 1965 and was completed in 1967, with major additions made in 78 and 95. Over time, the equipment may change, but the process has always remained much the same. This is at the beginning of the aeration basin, where the primary effluent, or water going out of the primary clarifiers, is mixed with the bugs, or bacteria found in nature that we referenced earlier. The water is pumped through this station and moved up into the aeration basin. There are 3 screw pumps involved in this process that measure 7 feet in diameter, 35 feet long, and are capable of pumping 17,000 gallons a minute. If you have a 3-foot deep and 20-foot diameter pool in your backyard, these pumps could empty it in less than 25 seconds. Much like the lift station we saw earlier, this pump station is equipped with its own 100 kilowatt generator in the event of a power outage. The reason these pumps move so much water is that up to 400% of the flow is recycled for nitrogen removal. What we are looking at now is the aeration basin complex, where the biological treatment part of the process takes place. Each basin is approximately 260 feet long, 66 feet wide, and 16 to 20 feet deep. Each basin has a capacity of 2.7 million gallons of water. The Scumplex, as it's known, was built in 1994. It has 15,000 cubic yards of concrete in it and enough steel to construct 4 double-lane bridges across the interstate. The aeration basin contains all of the bacteria and biota used to treat the wastewater and remove suspended solids and biochemical oxygen demand, or BOD. The removal of nitrogen or ammonia from the wastewater is a requirement based on the discharge permit currently in place at the plant to protect drinking water and fish habitat. This particular aeration basin is capable of meeting that standard. The 4 blowers inside of this building are 700 horsepower, each capable of putting out 10,000 cubic feet per minute of air, enough air to empty a 1,200 square foot house in 58 seconds. Typically, no more than 2 of these blowers are running at one time. The green piping you see stretching horizontally is low pressure air piping. Each basin receives 5,000 to 7,000 cubic feet of air per minute to help support the biological life. The air that is piped through this system is generally a warm air, allowing the bugs to live and grow and break down the ammonia into nitrates. The warm air also keeps the water from dropping below 55 degrees, keeping the process of Mother Nature moving at an accelerated pace. Each basin contains approximately 2,500 ceramic diffusers to break up the air into little tiny bubbles so that the biological life can use the oxygen. The first part of each aeration basin is 700,000 gallons and operates as an anoxic zone or without oxygen. The second part of each basin is 2 million gallons and is aerated or oxic, meaning with oxygen. Once ammonia nitrogen hits the aerated part of the basin, it converts into nitrates by uptake with the oxygen. This is when the 400% recycling begins its process, this time landing in the anoxic zone, allowing the bugs to take the oxygen molecule off of the nitrates, leaving nitrogen gas behind. So in general, we nitrify in the anoxic zone and denitrify in the oxic zone. What we are looking at now is the bacterial flock as it mixes in the anoxic zone. It's attempting to coagulate or stick together. Without the giant mixers that are in these basins, the water would turn clear on top and all of the solids would settle to the bottom. This would not allow the bugs to make contact with the nitrates, thus not uptaking the oxygen off the nitrate molecule, and the nitrify and denitrify action wouldn't happen. While we have said that we are accelerating the process of Mother Nature, it's interesting to note that through the recycling process, solids remain in the system up to 16 days. There are several hundred tons of solids within this system, with only 2 to 3 tons being removed each day. Without the solids containing the bugs, there would be no way to treat the waste. It's ironic that removing the solids is the focus treatment in the beginning, only to be added back into the treatment process later to further treat the water by supplying food for the bugs. Who would have thought that removing the solids from the water is as vital as adding them back in? Once the water leaves the aeration basins, it goes back to clarifier basins, but this time they are final clarifiers. A fence surrounds each of the 3 clarifiers to prevent excessive wind loading on the surface. On a windy day, scum buildup will get pushed to one side and go over the edge, releasing solids with the final effluent, or water going out of the plant. The final clarifiers act very much in the same way as the primary clarifiers, with the only real difference being the depth. The deeper clarifiers allow more solids to settle out. These upright pumps are what move the solids from the final clarifiers back out to the aeration basins for recycling. Each one is capable of pumping 3 million gallons per day. The smaller pumps on the left are used to waste the solids out of the bottom of the clarifier and back to the waste sludge holding tanks we referred to earlier. Each of these recirculatory pumps has a price tag of over $20,000 apiece. According to the NDEQ, or Nebraska Department of Environmental Quality, the Wood River is classified as a warm water B stream, which means the effluent must meet warm water B stream standards for fecal coliform and E. coli. A UV disinfection facility disinfects the water as a part of the treatment process. UV is considered to be a very safe and efficient means of wastewater disinfection. Inside of the UV disinfection facility, we elevated a bank of UV lamps to help illustrate not only what is being used in this part of the process, but how they work day to day. The small circular white rings that are moving back and forth are actually cleaning the lamps. Each ring contains a scraper to clean the bulb. The center of the ring contains a lime-away gel to remove hard water stains off of the bulbs. The cleaning mechanism is powered by the hydraulic system seen here. The fluid used within this system is a food grade, which means if a leak were to occur, the employees and the environment are not harmed. There is quality control sampling and testing performed throughout the plant, but here at the final sampler is the most important sampling that is performed. This sampler takes a portion of the plant effluent, or water going out, with 2 to 4 samples every hour. Facility staff also test every day for BOD, suspended solids, nitrogen, and E. coli. Test results determine whether or not the plant is protecting the environment and meeting the permit requirements. This facility supports 240 feet of finger weir within the UV disinfection system. Under the grate, you can see the small channels that are a part of that system. A weir is an engineered system used to maintain a constant flow of water. It's in place to ensure that the flow of water being treated is not coming through the system too fast. In other words, every drop of water is receiving the same amount of exposure to the disinfection system to ensure permit requirements are being met. The flow that exits the UV disinfection system here on the northeast side of the building travels down through this junction box and out through this discharge, which contains again a partial flume. It continues down another junction box and out a 42-inch pipe into the storm sewer outfall ditch that is north of Swift Road. After all the treatment, this is what is left behind. At this point, the water is less than 10 milligrams per liter suspended solids and BOD. Ammonia in the effluent is generally less than 1/2 per part per million, which is much lower than what the facility permit allows. A mile east of the facility, the flow enters the Wood River. This completes the liquid portion of the treatment process. We still have to review the solids portion of the treatment process. The primary and secondary solids are moved to these 2 holding tanks, where they are stored and aerated before dewatering and later hauled to the landfill. The sludge runs through the belt filter press. The top, or yellow section, is the gravity belt thickener, where water drains out through gravity. The lower section, where the yellow and orange belts meet, is where the water is pressed out of the sludge. The dewatered sludge cake drops off the press to an auger that carries it to a truck. It's important to dewater the solids in order to keep the weight down of every load being taken to the landfill. This ultimately translates to money saved. By removing as much water from these loads as possible, it keeps the weight of the load down and in turn keeps costs down. It's common practice for only one of these 2 tanks to be in service on any given day. The second tank is now used primarily as a backup. Of course, the process is much more technical in ways that we can't even begin to describe, but what's important to remember: we should never take our water for granted, or the men and women who work so very hard to protect and treat it.
Okay, so when we consider the steps of wastewater treatment, a lot of the steps are spatially segregated, and they decrease the organic matter and the number of microorganisms in human waste impacted water, and it's led to a major reduction in pathogenic spread. So you can see here problems that are caused by the contaminant. Suspended solids can cause deposition of sludge, leading to anoxic conditions when you discharge it into the groundwater or the surface water. Biodegradable organics include things like proteins, fats, and carbs. If they're discharged into the streams and rivers, they cause heterotrophic growth, leading to anoxic condition. This is an example of a phenomenon we call eutrophication, where essentially we cause one component in the ecosystem to overgrow, and what happens is that we create a dearth of oxygen in, say, an aquatic ecosystem that only allows anaerobic organisms to take advantage of that niche, and that can produce extremely negative impact on the ecosystem. Pathogenic microbes cause infectious disease. The more we cut down on those, again, the safer we are all the way around. Priority pollutants include organic and inorganics that can be toxic, carcinogenic, mutagenic, or teratogenic, and again, microbial action can essentially render these harmless by essentially oxidizing them. And then there are refractory organic compounds like phenols and surfactants, pesticides that resist conventional wastewater treatment. And here we get into a little bit of what we call bioaugmentation, where what we like to do is try and isolate or engineer, in some cases, organisms that can break down these refractory compounds into something less harmful, which can be discharged in the environment relatively safely. Heavy metals are usually discharged by industrial effluents into rivers and streams. It's toxic at all trophic levels. We can use bacteria and fungi and plants as a way to reclaim these toxins and, as a result, repurpose the groundwater and the land. And then dissolved inorganic constituents, including calcium, sodium, and sulfate, can be added to domestic water supplies and have to be removed prior to wastewater reuse, due in part to the fact that they can serve as eutrophiants. They can also, at certain levels, become toxic. So what you're looking at here is just some of the primary treatment processes in wastewater. We remove solid material and form sludge in primary treatment, primarily by settling. We just use density to do its work. The sludge can then either be burned, or we can treat the sludge with microbes in order to promote degradation. There's a number of ways that this particular component of primary treatment can be rendered less toxic. Secondary treatment, dissolved organic matter is transformed into microbial biomass and CO2, and this forms floc that settles. Bulking sludge does not settle properly, so we have to have a system in place to deal with that. Activated sludge is facilitated by horizontal flow of material with the recycling of the sludge. And again, the sludge in some cases can simply be combusted. In some cases, we deal with it by breaking it down biologically. So here you can see sort of an overview of a waste treatment plant. The MSD over on Guest Street locally has all these features. If you're interested, they do conduct tours. You can see here with the primary treatment, we're primarily getting rid of insoluble particulates by screening and using precipitates. Alum and other coagulation agents cause tiny particulates to become large particulates, and then it's easy for that to settle out. Those big tanks that you see in the picture in the upper left are settling tanks, most of them, and then the ones that have the ones that are big and circular, some of those are used for aerobic breakdown of toxins. Some are settling tanks. Secondary treatment, we have biological removal of dissolved organic matter. We can use filters, we can use sludge, we can generate lagoons, and we can have extended aeration system and also anaerobic digesters. One of the things we have to appreciate is that you're going to have a whole community of microbes that are going to be active in different parts of this wastewater treatment niche. The aerobic bacteria are going to be active in areas where oxygen content is high to medium, and then the anaerobic bacteria take over where the aerobic bacteria can't persist, and they continue the breakdown of these effluents. And tertiary treatment is biological removal of inorganic nutrients and chemical removal of inorganic nutrients. We also remove viruses, and we also trace chemical removal. So we use a combination of chemical and biological treatments to facilitate the whole process. So here you can see the trickling filter. The waste effluent is passed over rocks or solid material with microbial biofilms, and the community breaks down the organic waste. Extended aeration reduces the amount of sludge produced by using microbial biomass for energy requirements. So basically the bacteria are here doing the work. The oxygen speeds up their metabolism and speeds up the degradative process. In anaerobic digestion, we see high efficiency anaerobic systems that are used for sludge digestion and methane production. This is a system that's been put to work in Germany, The units are well insulated so they maintain their temperature without outside heating, and the methane can be burned and used to generate electricity. So we kind of repurpose some of the byproducts of the breakdown and can use that to, in part, power the plant. So you can see here how it works. Often the sludges from the aerobic sewage, together with materials that settle out in primary treatment, are subjected to anaerobic breakdown. The anaerobic microbes can do things that the aerobics can't, and this again renders a lot of the toxins oxidized and relatively harmless, and then we can pass it on to the next phase of treatment. The bottom line is we want to reduce the amount of sludge that we have to dispose of, and we can of course repurpose the methane. Tertiary treatment is essentially the removal of nitrogen and phosphorus that can promote eutrophication if it's out there in the environment. You've probably seen eutrophicated water systems. They usually have large algal mats growing on the surface, producing anaerobic conditions beneath them, and the impact on the ecosystem is quite negative. This happens as a result, for instance, of fertilizer runoff from urban and suburban lawns and farms into our waterways and into our groundwater, and it's incumbent on us again to try and get rid of as much of this stuff as possible so the ecosystem remains relatively unperturbed. It also removes heavy metals and biodegradable organics and remaining microbes, and we can use artificial wetlands as a way to deal with tertiary treatment. They've used this successfully in places like Florida, where we treat the liquid wastes by generating a combination of plant and microbial populations in a natural setting that can use the wastewater that comes from the secondary treatment and serve to purify it, similar to the way, honestly, that it works in nature. And obviously what we have to do before we release the water back into either the surface water or the groundwater is we have to test its quality. We use total organic carbon levels. The oxidation of carbon to CO2 can be measured by infrared, and there are chemical oxygen demand tests that we can do. Biochemical oxygen demand measures the carbon oxidized by microbes at standard conditions. These methods do not measure nitrate, phosphate, or sulfate levels, which again can promote eutrophication in groundwater or surface water. Now, home treatment's a little different. Groundwater in gravel beds below the surface soil can use microbiological processes that are not well understood in order to render it relatively harmless. Septic tanks are used for sewage that they frequently fail to work, and this can contribute to contamination in the groundwater. So what are some of the challenges that lie ahead with bioremediation? You think about the growing population. If we want to provide potable water for 7 billion people, this is a considerable challenge. Water reuse via purification of wastewater into drinking water has been employed when the available water, the potable water supply, is at a premium. Complex processes are often required to get rid of pathogens and pharmaceuticals, but these systems do work. Sewage overflow during storms due to stress capacity of municipal systems is a growing problem. One of the reasons for this is that we've gotten rid of a lot of the components of the soil, and we've replaced it with asphalt. And so what happens when it rains is that you get a lot more runoff than you would normally anticipate. So you don't contribute adequately to the groundwater, and you pollute a lot of the water that hits the concrete and the blacktop, and that goes into the municipal systems, and the result is that we have frequent overflow. We've generated basins and increased infrastructure to deal with this, but sometimes we exceed its capacity. So next thing we want to do is describe the importance of certain chemical processes that take place in biodegradation and bioremediation, understand how they work. We'll talk about dehalogenation. We'll discuss factors that influence the rate of biodegradation and bioremediation in a compound. We'll talk about how endogenous microbes can be stimulated to break down environmental pollutants. That's similar in a sense to what we're going to be doing in lab. And we'll talk about the rationale on which the addition of microbes and microbial products to contaminated soil and water is based. So, the metabolic activity of microbes can be exploited in natural environments where physical and nutritional conditions for growth can't be controlled. A largely unknown microbial community is already there and can take advantage of compounds that are considered toxic or deleterious. Examples include the use of microbial communities to carry out biodegradation, bioremediation, and environmental maintenance, and the addition of microbes to soils or plants for the improvement of crop production. So we're looking here at an example of biodegradative pathway. There are at least 3 definitions of biodegradation: minor change, fragmentation, and mineralization. You can see examples of each here. This is an example of dehalogenation. Remember, the halogens are the second to the last column in the periodic table. Halogen means salt former, and halogenated organics are a major toxin. However, bacteria can remove these halogens from these microbes and generate byproducts that are a lot less toxic. These are non-substituted phenolics that are going to be a lot more amenable to further oxidative breakdown by other components in the community once the halogens have been stripped off. In this case, the chloride is relegated to its anionic form. Fragmentation is just exactly what it sounds like. It's the breaking apart of a large molecule into smaller component pieces, and this sets up subsequent enzymatic reactions that can ultimately break this all the way down into electrolytes and oxidized organics that are available, again, for metabolism. And then here you can see mineralization, where we literally take the compound all the way down to its component parts. You can see that the carbon component is going to be completely oxidized. The halogens have been stripped off, and we've made also water as a byproduct. So no organic material remains on the right-hand side of the equation. And you can see that you could have a combination of these metabolic pathways within a single microbe or between microbial communities, where one community will create something useful by another component in the community, and eventually what will happen is we can break this stuff all the way down to its least hazardous components. So bioremediation is simply the use of microbes to turn toxins into non-toxic degradation breakdown products. The degradation of toxic molecules usually is a multi-stage series of chemical reactions. Enzymes, of course, catalyze most of this. Different microbes can carry out different parts of the biodegradative process. In reductive dehalogenation, we strip the halogens off of a halogenated hydrocarbon, and we generate now a hydrocarbon that can be immediately shunted into other available metabolic pathways. Here we can see the dehalogenation of a hydrocarbon generating now an alkene. Alkenes contain considerable amount of chemical potential energy, and there are an abundant number of microbes that can use this directly as an energy source. This generally occurs under anaerobic conditions, so oxygen is at very low levels. Essentially, when we're stripping this off, what we're doing is we're oxidizing here the hydrocarbon, and we're actually reducing the halogen. Okay, and so what we're making here either is the anion, or in some cases the gas. The stereochemistry and the molecular structure of a compound play an important role in predicting what's going to happen to it in nature. The meta effect occurs when the constituent is in the meta position, and by meta we mean its position on a benzene ring, and I'll show you what that is in just a minute. Um, if it's in the meta position versus the ortho position, the compound is more difficult to break down simply because there's fewer enzymes, known enzymes, out there that can deal with compounds that are substituted in that matter. A lot of compounds added to the environment are chiral, so they have asymmetry, and the result is that they're often not enzymes that can effectively break down those compounds due to their difference in shape. Microbes often only degrade one isomer of a particular substance, and the other will remain in the environment. So here you can see an example of how the chemical breakdown of a toxin can change depending on the exposure of the microbial community to that toxin over time. So here we see in blue the initial degradation pattern, where the amount of herbicide persisting in the ecosystem is on the vertical axis, the amount of time it takes to break it down here on the horizontal. And you can see that under the initial exposure, it takes a lot longer to break this particular toxic component down. But what happens as a result of that initial exposure is that we select for organisms that can take advantage of some of these intermediates, and we enrich them. And so what happens the next time that particular toxin is reintroduced into that same microbial community is it degrades at a much quicker rate. So this is an example of selection and in a sense augmentation, okay, because what we're doing here is we're producing conditions that are going to favor those organisms most likely to break down this particular set of compounds. Microbial communities change their characteristics in response to their exposure to these chemicals. Acclimation occurs if the chemical is repeatedly added, so the community will adapt at faster rates, and the degradation will occur much more quickly, and that's what you saw in the previous plot. But there's a downside to this. It can lead to widespread damage and financial loss if it occurs in inappropriate situations or in an uncontrolled fashion. Example would be the corrosion of metals, for instance, iron pipes and toxic breakdown products. So here you can see some examples of some toxic breakdown products. This is DDT, a potent insecticide, and this is one of the breakdown products, DDE, which is also relatively harmful. TCE can be converted into vinyl chloride, still a potent and persistent organic pollutant, POP. Bioremediation involves stimulating degradative activities of microbes that are already present at the site. It's necessary to determine the limiting factors at the site and supply them so that we've at least satisfied the initial conditions for breakdown. Co-metabolism is the addition of easily metabolized organic matter that increases the degradation of the compound that we're targeting. It's not usually used as a carbon or an energy source. So you might have a compound that you really want to dump, okay, really want to clear it out. And what you need is, you could think of it as some organic compounds, or in some cases some inorganic components that prime the pump, so to speak. The idea here is that they could serve as a component in one of the bioremediated pathways, and once that missing component is supplied, then that particular set of microbes can begin to break down that toxin much more rapidly and predominate in that community. So here's some examples. This is stimulation of hydrocarbon breakdown in water and solutes. We can also use plants to do this. Phytoremediation is what we call it when the plants get into the act, and we're going to see in a bit a video on mycoremediation using fungi to try and remove these persistent organic pollutants. Stimulation of bioleaching of metals from minerals, another example of detoxification of industrial effluents. Again, the idea here is that the microbes can reduce the adulterated effluent or the adulterated ore, and we can extract now the metal in its pure form and then repurpose it. Surfactant production, you can see here, increases the surface area necessary for the microbes to do their work. And by microbe, we're using kind of a catch-all descriptive term to cover phage, bacterial, and protozoal activity, all working together to get rid of the persistent organic pollutant. So you can see here an example would be oil. Okay, surfactant production is going to increase the surface area available. We're going to have degradation intermediates, and then the secondary consumers can come in and do their trick with the increased surface area. Other components of the bioremediative community can also contribute. Bioaugmentation is a different story. In bioaugmentation, what we do is we try and go out and find organisms that are specifically adapted to break down our target compound. And what we do is we introduce them artificially. It generally results in short-term increases in the desired biodegradative activity, and the outcome can be improved by improving or providing protective microhabitats, such as biofilms or living microhabitats, such as seeds or roots or leaf litter. Natural attenuation is the use of a natural microbial community to carry out the biodegradative process. Essentially, we use what's there, and by selecting over time, eventually we're able to get rid of the POP. So here's a look at bioremediation in general.
Good afternoon. I'm Shelly Mahendra, and although I'm a city girl, always been, I would love to live in a place like this, clean, green, pristine environment. Well, let's face it, a lot of our environment is dirty. And in addition to the trash and the piles of dirt that you're seeing, what we don't see is the water resources, the soil and groundwater is also contaminated. It is my job to take this back to clean environment. So I do that at UCLA in my research. I'm an assistant professor in civil and environmental engineering. The conventional technologies to clean groundwater specifically sometimes just don't work. There are air stripping towers, there's carbon sorption, don't always work for all kinds of pollutants. The technologies that do work are extremely expensive when we're dealing with vast volumes of really polluted water. What we do sometimes is move pollution from one place to another. But that doesn't get rid of the hazard. The poisons are still there. In light of all this that we know that doesn't always work, my research group, we are evaluating bioremediation. Tell you what bioremediation is. In situ, that means we work at the site that's contaminated. We don't have to truck garbage or water or dirt from one place to another. Bio, which means we use microbes, microscopic critters, bacteria and fungi to do their job right there in the environment. And remediation really means to restore or fix, so we can take contaminated environment back to clean environment. Specifically, we look at the next generation of contaminants that are going to be found in our drinking water. One of the things that we look at are called perfluorinated compounds. They're found in firefighting foam and nonstick cookware and a variety of scratch-resistant coatings that we have. Also nanomaterials, they're used in a variety of applications, from titanium dioxide in sunscreen, silver in our washing machine, nanotubes in electronics, and automobile applications. We think that in another few decades, 2 or 3 decades, they're going to be found all over the environment. And we don't know how much there's out there, what it can do to us, or how to deal with this, deal with that potentially toxic substance that we are adding to the environment. Today, I'm going to tell you about a chemical, 1,4-dioxane, that I worked with for about 10 years now. 1,4-dioxane causes cancer. It's a common industrial chemical that's found in a variety of applications: paper manufacturing, solvents, filters, cellulose, textiles. It's also found in our personal care products, lots of cosmetics, makeup, baby shampoo, lotions everywhere. So we are being exposed to it. And I just told you, it causes cancer. So one way where my research group, all of us work together and we work on bioremediation of 1,4-dioxane. 1,4-dioxane, as I said, it's commonly found. When we look for it, we find it everywhere. It's a common groundwater pollutant. It's infinitely soluble in water, so it just travels with water, and it has a potential to impact large number of people, large number of places rather quickly. So it's ideally suited for in situ bioremediation. This is an organism we work with. It's called Pseudonocardia dioxynivorans. This thing makes a living out of eating dioxane. It eats dioxane. It loves dioxane. I've worked with it. I characterized this bacterium. Isn't that a good-looking bacterium? And I even got to name it, Pseudonocardia, that Pseudonocardia that voraciously eats 1,4-dioxane. Recently, together with other collaborators, we sequenced the entire DNA genome of this organism. So now we know what the secrets the DNA holds and how we can put it to use in actual field application of bioremediation. My research group at UCLA, we develop omics-based tools. We know about the DNA. We can use genomic information. We can use gene chips, messenger RNA, transcriptomics. We understand the protein profile when it's working. We also understand the metabolic pathways. How does it all work? How can this thing make a living out of eating dioxane and then help us humans clean our environment? It seems to be a win-win. It's fascinating. Another thing that we do is we monitor dioxane and the progress of bioremediation using something that we call stable isotopes. And I'm going to use this jelly bean analogy. As dioxane is removed from our environment, the total number of jelly beans, they go down. But it could happen with any combination of random environmental processes. To confirm, to make sure, to validate that bioremediation is indeed happening, we look for signatures, and they are different for every compound. So in this case, as the total number of jelly beans goes down, and it gets richer in the red jelly beans, the white get eaten faster than red ones. That's a very solid proof that indeed in situ bioremediation is happening. And that's the kind of work that I do in my lab. So with help of awesome students and colleagues and sponsors, I hope to take my work from the field, from the lab, into the field and actually make a difference. Thank you very much.
Okay, and here's a look at mycoremediation.
Ecuador is known for its incredible biodiversity due to being where the Andes meets the Amazon. This vital ecosystem has been exploited, and few realize the true devastation that has occurred. For over 40 years, oil has been extracted from the jungle. Once pristine virgin forests and rivers, they are now contaminated. Unlined waste pools still exist, which continue to overflow and seep down into the water table. Between 1964 and 1992, Texaco spilled over 18.5 billion gallons of toxic waste into unlined pits. Most of these remain untouched, although there have been attempts of remediation using bacteria, but this has not shown completely successful results. A need for a more effective method was necessary.
Queremos es que nos limpien estos pozos que han dejado de petróleo contaminado, que hace mucho daño tanto para uno como para los animales. Y contaminan los ríos también, porque aquí muy cerca hay un río y eso va contaminándose por dentro de la tierra. Por ejemplo, cuando está muy fuerte el sol, eso evapora, se apercibe. Si uno va pasando por ahí, apercibe. Y eso da mareos, da dolor de cabeza. También de las aguas salen manchas en el cuerpo, da unas comezones. Que ya sea el tiempo que hagan algo por los campesinos, es lo que se dice, ya que nos han dejado contaminando nuestros terrenos. Sí.
And we used this oyster mushroom in order to produce spawn to do bioremediation on this oil tank. Right here, this is the culprit, 500 gallons of diesel.
After hearing about mycoremediation, the use of mushrooms to break down hydrocarbons, the question was whether or not this technique would work in this environment. Studies around the world have shown mycoremediation to be up to 95% effective, but never before had it been documented in the Amazon. So there was only one way to find out: to start trials here in the Ecuadorian Amazon. A team of experts donated their time and energy to come down to Ecuador to implement these trials, to discover with scientific testing if this method of remediation could truly help with the cleanup of the contaminated sites. The team soon got to work, sorting out the logistics. First, they went to look at a number of sites to discover which would be the best place for the trials.
Right next to the water.
You can clearly smell the petroleum in this soil.
After discussing the ideal location, the team got to work, unloading the 300 kilos of mycelium that would be used in the trials and building the necessary infrastructure. Half of the burlap bags were pasteurized with a weak hydrogen peroxide solution to see if this would help and give our mushrooms a better start without the competition from other fungi and bacteria. The bags were fully rinsed and left to drain.
This looks like it's perfect for our needs for remediation. Fungi will grow on this, and it's a great mixture of sawdust and more bigger pieces like this. It can also be great mulch to put over the installation so that we can just keep it from the sun, and it's good substrate, good food for the mycelium, and there's abundance of it here, so we'll be able to use it for our purposes for the site. The first step in this process is taking cardboard, wetting it, and ripping off the smooth layer to expose the corrugations. The mycelium will grow well on this corrugation because there's increased edge. And where there's edge, there's diversity of habitat, from moisture to humidity. We add the inoculated sawdust onto this moist cardboard and then fold it, creating a microclimate for the mycelium to grow. Then we add about 10 of these myceliated cardboard packages into this burlap bag that's been inoculated with sawdust growing mycelium. There's also straw, wood chips, and sawdust that has not been inoculated in this bag. We take these little packages and put them deep within the burlap bag so that the mycelium can grow from the very fine material, like the sawdust and the cardboard, onto something more dense, like this dense piece of wood. The bags and the substrate within the bags are wet because the mycelium typically like a moist environment to grow. And we're doing a high spawn inoculation rate because this is a low-tech method of inoculating mushrooms onto substrate. Usually it's done in a lab with high intensive heat, beat, and treat methods to sterilize the media. But we are passively pasteurizing the media in order to eliminate competing bacteria and fungi. And we're putting 8 kilograms of mycelium in each one of these bags, along with about 10 of these little packages of mycelium. So hopefully the mycelium will really take root in this bag and grow to colonize the whole bag, producing enzymes as they break down the substrate, the straw, and the sawdust. And those exudates, or those exoenzymes, will wash down into the soil, breaking apart the hydrocarbon molecule.
Passing the local disused station, it was time for the team to head out to begin the installation.
Well, we just got out to the site checking out this pool, and this has been this way for 30 years, where this oil has been dumped into this pool here, and there's a channel that leads off so that when there's heavy rain, the water will flow into that channel and then the river will take it down. So you look at it and there's vegetation, it looks like dark earth, but then poking at it and getting a chance to see what's there is there's clearly crude oil underneath the ground, just a couple inches, and water. So you know that the water underneath the ground is just channeling it over to this channel, and that the oil has just stayed here for 30 years. So it's definitely toxic to wildlife, it's toxic to the people that depend on this part of the jungle, and there's techniques that we've discovered and that others have worked with for a long time that could metabolize this oil and this crude and break it down before it reaches the river.
Well, I'm kind of shocked to find something in the middle of the jungle. It's it's so industrial in character. It isn't a natural pool of any kind.
I think I'm pretty shocked to see a site with like solid tar and product and continual sheen pouring out just sitting here.
Have you ever seen a site like this?
No, never. Never. It's terrible.
If I were looking at this same site in the United States somewhere, there would be hazmat crews out here, and they'd be spending millions of dollars.
Estoy bien impresionado sobre esto que hemos visto por primera vez, los derrames aquí. Siempre hemos visto cerca de la carretera derrames que rápidamente lo limpian, por lo menos parece que lo limpian. Pero acá estamos viendo el petróleo de 30 años que está regado. La gente invierte tanto dinero en esto, gana muchísimo dinero más y no puede gastar un poco de dinero en limpiar. Dañan mucho a la gente, dañan nuestro ecosistema y todo el mundo sabe de esto y no se hace nada. Ahora el trabajo está en tratar de limpiarlo, no puede quedar más tiempo así. Tenemos que ver la forma de remediar, de limpiar nuestra tierra para que la gente ya no se enferme con esta basura que dejan las empresas petroleras.
En el Ecuador es muy típico ver los derrames de petróleo. Es necesario hacer algo y es por eso que hemos puesto los hongos en manos para el control de este tipo de contaminación. Creo que es compromiso de todos nosotros como ecuatorianos, uniéndonos con manos extranjeras, hacer algo, ya que muchas empresas irresponsablemente dejaron derramado el petróleo. Es tiempo de actuar.
We've taken burlap bags that are filled with sawdust, straw, and wood chips, which is an excellent food source substrate for the mushrooms to grow on. And we've made 3 plots that we've surrounded by other burlap bags. On top of the 9 burlap bags that we placed, we filled 9 other burlap bags with contaminated petroleum from this site here. We dug back some of the vegetation, and there's visibly, and you can smell the oil that is near the surface and deep, deep below the levels here in these pools. So we have these burlap bags that are filled with the oily, contaminated soil, and what we'll do tomorrow is we'll take the burlap bags that have sawdust and straw and wood chips that have been inoculated with mushrooms, and we'll add that on top of this contaminated, oily product that's in these burlap bags. The intention is to see if the enzymes that the mushrooms produce as they break down the substrate, the sawdust and the straw and the wood chips, if those enzymes will also be capable of breaking down the petroleum hydrocarbons that is here in this unlined pit, this pool that's filled with oil here in the jungle. We have this oily soil that we've pulled up from the pool, and these soil samples will be sent on ice to the lab in Quito, and we should have results with what our baseline testing is within the week.
Both the soil and water samples will be tested for levels of hydrocarbons and heavy metals. The testing is then carried out every 3 weeks for a 3-month period to monitor the results. The final part in the installation was to lay the bags filled with sawdust, straw, wood chips and the mycelium on top of those filled with the oily crude. Using this simple, cheap and effective method, we can show how low-tech this amazing permaculture technique really is. Creating a runway, we hoped the additional mycelium could then run towards the pool. Finally, the test site was covered with straw and a shade cloth to help keep the moisture in. Our group had comprised of a diverse gathering of individuals from different countries and different walks of life, each with their own expertise and commitment to help make the world a better place.
So it's been 3 days since we installed, and the bags are still wet and moist, and mycelium is starting to run and form in the bags and even on the burlap sacks, like from the mycelium that's inoculated just in the sawdust, and the packets look good. So it looks good. Yeah.
In these boxes, we put the crude that we extracted from the site, with a mixture of substrate and packages of mycelium, and we added more sawdust and straw to the top to keep the moisture in. There is the control box and a number of boxes treated in different ways, so we can watch to monitor the difference in the breakdown of the hydrocarbons. Once the remediation is complete, the mushrooms will be composted and hardwood trees will be grown. These trees will then absorb the remaining heavy metals in their growth.
This is our contained experiment that we'll be monitoring weekly. It's covered to keep rain and wildlife out, and it will be watered once a week and checked on. Pictures will be taken, and we'll be able to view how the mycelium is growing and also smell once the odor of petroleum is gone.
Chevron Texaco carved roughly 1,000 open-air waste pits in the jungle. Most still remain. Apart from these pits, there is the constant threat of new oil spills from old broken pipelines. We must look to the solutions of firstly replacing old infrastructure, using appropriate and efficient remediation techniques, and training locals to become emergency remediation crews. The aim of this project is to teach the locals not only about remediation, but also how they can grow edible and medicinal mushrooms for their own use and for sale. Courses will be regularly held, and if you are interested in finding out more, please visit our website, amazonmycorenewal.org. This trial has been the initial seed, but will show that we do not need to use chemicals or expensive techniques. We have the natural tools to start cleaning up this beautiful planet where we reside.
Okay, bioleaching is the use of microbes that produce acids to solubilize metals for recovery. It's used in mining areas with levels too low for recovery by smelting, which is essentially a process of heating the adulterated ore so that the heat of vaporization at different temperatures produces different components that we can then drain out of this essentially blast furnace. It's not a useful technique when you've got very tiny amounts of the recoverable metal. So what we use is bacteria to try and do the trick for us. Leptospirillum species and thiobacilli can be used to recover copper. Other types of bacteria can be used to target other metals. Okay, so we get now to the last part of the talk. We're going to deal in the lab with oil-eating microbes. We'll be growing them in a flask from a powder. Essentially all you need is sterile water, sterile flask. You add the powder and you'll generate now a milky suspension after shaking them 2 or 3 days. Once you've got your milky suspension, you've got essentially your pilot culture, and what we're going to do is we're going to grow one culture in just water, one with oil, and then we're going to do an experiment where we're going to change the pH of the oil-water mixture and determine at what pH the bacteria were most effective at breaking down the oil. And the way we'll do that is kind of indirectly. We'll look at the amount of oil remaining, but the other thing we'll do is we will do an OD to look at the number of bacteria in the flask. In addition, we're going to stain for the bacteria in the liquid culture and try and get an idea which culture contained the largest number of bacteria, and we can impute from that what the optimal conditions might be. And so this is just a flow chart showing you what we're going to be doing in lab with the OEMs. We start again with the starter culture, and then we're going to get our water and oil, and then water and oil at different pHs. And then what you're going to do is grow those up. We'll do an OD 600 on the liquid culture versus a water control, and we'll determine the overall OD, and then we'll stain, and we'll see what kind of bacteria we pick up. We'll use gram stain for this. Okay? All right. I'll see everybody in class, and have a nice evening.